Now. Good. So once again, thank you very much for joining us today for our 26th seminar in this series. It is a seminar series on physics-informed machine learning meets engineering, which is organized at the Alan Turing Institute in London, which is the UK's national institute for AI and data science. My name is Zadawar. I'm a PhD student at the Turing, and I'm joined by Andrea Pizzaferrato, who just gave a wave, who is a researcher at the Turing. So if you would also like to speak in this seminar, please feel free to get in touch with us. It is a seminar where a speaker talks about for 45 minutes, and then we have a Q&A session where you can ask questions either by using the raise hand button or typing it in the Zoom chat, and we will read the question for you. So to prevent any further delays, I will introduce our speaker, Lorenzo Branca, who will give us quite a different application of machine learning, which I think will be new for most of us here. He's a fourth-year PhD student at the University Scuola Normale Superiore di Pisa in Italy, where he is working on physics-informed deep learning methods applied to astrophysical simulations with a particular focus on thermo-chemistry. And before that, he studied for a master's and bachelor's degree in physics, astrophysics, and space physics at Milano Bicocca, where he was working on thermodynamic decoupling condition of neutrinos and super Eddington accretion on supermassive black holes. So I hope that you will enjoy the seminar, and I will mute myself so that Lorenzo can start.
Okay, thank you for the introduction, and hi all. Thank you in particular to you, Zach and Andrea, to invite me. So let me share my screen. Okay. Okay. Okay, can you see my cursor on my screen?
Yes, all good.
Okay, so we can start. Thank you again. And today I will tell you something about my recent work, and also in the end of the talk, something about what I'm working currently. The topic of today will be the following: emulating interstellar medium chemistry with physics-informed neural network. First of all, I want to give you a little overview. First, in what kind of context we are in the context of realistic astrophysical simulation that we researchers in this field heavily used to theoretically model what happens in the universe. We will see it later in more detail, but in particular I will focus on integration of full non-equilibrium thermo-chemical evolution of the gas in the simulation that can present several issues, and we will see it. The aim of my recent work is to develop a deep learning based emulator to replace classical procedural solver to speed up simulation, and we will see. Since this meeting is related, I have probably an astrophysical background. I just quickly introduce the environment. So this is a nice cartoon that shows the evolution of our universe according to the standard cosmological model, lambda CDM. I don't want to go in deep, but what do you need to know is that at some point in the history of the universe, after a couple of hundreds of million years, some structures starts to form, and we call this structure galaxies. This is a typical spiral galaxy, like our galaxy, the Milky Way. And what is important is that galaxies are formed by gas, and in the more dense regions of the galaxy, something happens. In particular, stars can born. This is a zoom in and represent a particularly dense region of a galaxy, and we call the gas of this region interstellar medium. So when I am saying interstellar medium, I mean gas. This is particularly important for us, as I was saying, because it's the place in which stars can form. To be more precise, let's talk about this interstellar medium. Here you can see a snapshot of a simulation performed by our collaborator in 2020, Davide De Cataldo, and represent the gas density in a so-called in an environment that is named the molecular cloud. This is because this gas is made by hydrogen, helium, but in this kind of environment, a significant fraction of the hydrogen is in molecular form. To describe it, of course, we heavily use numerical simulation. This particular example is a medium-sized simulation. It's of 10 to the 8 finite elements, but it is AMR. It is performed with an AMR code. So during the simulation, the grid will be refined, and overall, it took 350,000 CPU hour. Let's see what means simulate the interstellar medium dynamics. We need some ingredients. First of all, we need the gravity, because this environment have a self-gravity effect, and the gravity is described by the Poisson equation. In computational terms, solving the gravity required just the 10% of the total computational time, so it's not so demanding. Of course, we need to solve the fluid dynamics of the gas. Usually we solve the Euler equation, and it took the 20% of the total computational time. In this snapshot, you can see some black points. That points represent stars that can form in the interstellar medium, and if a star's born, it emits light, of course, and the light interact with the have an interaction with the gas itself. So to properly describe the evolution of these clouds, we need to solve on the fly the radiative transfer, and it requires also kind of 20% of time. I told you before that the gas is made about hydrogen, helium, molecular hydrogen, of course the ion. So to properly follow the evolution of this environment, we also need to follow the chemical evolution of this environment. And so we need to couple this kind of hydrocodes with a solver for the chemistry. Unfortunately, solving the chemistry is not so easy, in the sense that it will require a lot of time, even with a simple chemical network. And now we will see why. But first, let's go a bit in deep in the description of the chemistry of the interstellar medium. This is a graphic representation of a typical chemical network that we use in our simulations that describe the reactions for the hydrogen and the helium chemical network. Each arrows represent a chemical reaction. But to be more formal, these are the equation set that you have to solve to follow the full non-equilibrium thermochemistry. The first equation is actually an ODE system. The index K represented a particular chemical species. And And this is the equation that regulates the time evolution of the number density of this particular species. The bottom equation is the equation that regulates the temperature evolution. On the right-hand side, we can see the first term of the upper equation is the two-body reaction rate term, and this guy A contains the all the reactions rate. The second term is the ionizing processes rate, and it describes how the incident radiation interact with the medium and potentially can ionize a particular chemical species. The equation temperature is completely described by two terms, the heating and the cooling term. All these equations are coupled because the two-body reaction rate is temperature dependent, and both the heating and the cooling term are temperature dependent and potentially dependent on the number density of some particular species. So we need to solve all this set of equations simultaneously. But we can have some problems in doing that. There are two main computational problems in solving on the fly the thermochemistry of the ISM. The first is about the timescale. The typical timescale for a chemical reaction in this kind of environment is much shorter respect to the hydrodynamical timescale of the simulation that is in some sense the reference time of the simulation. This means that to follow properly the evolution of the number density of the species, we need to subcycle an implicit solver. And of course, this could be very demanding in terms of computational time. The second problem is more related to the complexity of the ODE system itself, because as you can imagine, if I increase the number of the chemical species, the number of reaction grows and grows more than linearly. This means that if we have a relatively large chemical network, we have a fast-growing floating point operation that we have to solve, and this is demanding itself. Another problem is the so-called load balancing problem, because of course these are massive simulation. We need to parallelize on several CPUs, and unfortunately, in the simulation box, the thermodynamical state of the gas could be different, cells by cells, I mean, and with a different thermodynamical state, the solvers can require a different time, and this causes load balancing problem and slow down all the simulation. Okay, in few words, I mean, solving chemistry in hydrodynamical simulation is a complex task where the state of the art is limited because it is very demanding, and so people are start to think about alternatives to directly solve the ODE system associated. In particular, people are thinking about fast emulators. And since we are talking about a differential equation system, one of the natural choice could be to use physics for a neural network. I'm not going to explain in detail the physics for neural network algorithm. I suspect that most of people here are quite familiar with it, but just in a few words, sorry. If you have a differential equation system, both PDE or ODE, with well-defined boundary and initial condition, if you are able to define the structure of a neural network in a way in which sorry, let me rephrase. If you are able to define in a correct way in your network, it potentially can represent the underlying solution of the differential equation system and its derivatives. And so that means that potentially we can define a loss function made by the residuals of the differential equation and optimize this loss function with an optimization algorithm by varying the neural network parameters until convergence. And in the end of the day, if we are good enough, the neural network that we trained, the trained model, would represent a good approximation of the differential equation solution. Okay, this is the general, I mean, the general picture of physics for neural network, but now let's go to see our particular case. We did a proof of concept work in which we consider two different chemical networks. One we call atomic. It's a chemical network that contain electrons, hydrogen, helium, their ions, and another more complex chemical network that also contain molecular hydrogen. You can see that with just two more species, the number of reaction grows by almost a factor 2. In this case of study, we also consider several heating and cooling processes that regulate the temperature, like photoheating. That means heating by photons, as an endothermic chemical heating and cooling, metal cooling, and so on, several processes. We also split these two cases in other two. So in the end of the day, we want 4 models. First, we call a single model, and is a model with fixed initial conditions. So a fixed initial temperature, a fixed initial total number density, and a fixed relative fraction for each chemical species abundance. And the most interesting one, that is the general case in which we want a model that is able to predict the results in a range of initial conditions for temperature, number density, and fractions. Of course, I mentioned before that we have also photoreaction in the equation, and for this particular case of study, we took a pre-computed radiation background, so we have not to compute on the fly for now, but in the end of the talk we will see how to generalize it. That in few words means that the photoreaction rate are pre-computed. I also want to spend a few words on what kind of equations we are talking about. This is an example. This is the equation that regulates the electron number density variation during time. You can see it's not the easiest equation ever. This red part represented two-body reaction term. So is proportional, each term is proportional to a product of two relative abundance of two different species or the same species in some case, and to a coefficient k that is the two-body reaction rate of a particular chemical reaction. And the second part that represents the ionization processes, and here each coefficient k are proportional to the cross-section between a photon at a specific frequency and a particular chemical species. Regarding these coefficients, the two-body reaction coefficients, they are temperature dependent and in general could have a not trivial dependence and not trivial temperature dependence. As you can see, this is an 8-degree polynomial in some sense. So we are not speaking about the easiest equation in the world. Okay, let's generalize this evaluation and see what is easy, what is not. First of all, we have an ODE system. And if you give a look in the literature, the most of cases in which physics for neural network are used concern partial differential equation systems. So this means that our case in this sense would be easier. However, we want a model able to predict results in a wide range of initial conditions, at least in the general case that I mentioned before. We can have an incredibly stiff ODE system. Potentially, we have a large number of equations, and as you can see in this plot on the right, there is a non-trivial dependencies between reactions rate and the temperature that can vary by several order of magnitude. Okay. In the end of the day, what we want is a model that, once trained, takes in input a particular value for time, so a time in which we want to know the evolution, and a particular set of initial conditions for the species, and give us the evolution, the number density evolution of each chemical species, and the temperature evolution. What we learn working on this topic is that a simple vanilla physics for a neural network architecture is not able to solve this task. With vanilla PINN, I just means architecture like I showed you before. So we developed a specific architecture for this task. That is this guy, and it is based on DGM layers. DGM means deep Galerkin method layers. Is something similar to long short-term memory architecture. I don't want to go to the detail. You can ask me later if you want to know a bit more. But what I want to say is that this particular architecture is developed to capture the sharp turns in the solution. We also adopt other technical trick. For example, we used an adaptive activation function in the layers. This parameter A is an adaptive parameter that changes the value during the training. Also, we, of course, used an adaptive algorithm to change the weights associated to every terms in the loss function, because if not, it would be difficult to for the algorithm to solve properly all the equations, because the residuals could be small if a piece is not very abundant, but that this doesn't mean that the equation that the model is learning how to solve the equation. So we have to balance all the terms. Okay, we developed this architecture, and for who is interested in software, I used a tool developed by NVIDIA. It is called Modulus. That is a tool specific for physics for neural network, and also for some other thing. Very nice and very fast in running on NVIDIA GPUs. Okay, I'll give you some results. I just want to spend a few words on the training phase. In this upper plot, you can see the loss function evolution during the training. As it's clear that if the model is more complex, the training is harder. There is a clear hierarchy between the models, from the simpler, this single atomic, to the hardest one, this general molecular. that is the most interesting. And it requires almost 10 million epochs that in real times mean almost 2,000 GPU hours of training. It is quite expensive. In this plot, in the second plot, you can see the kind of residual distributions for all the models when I stop the training. And in this multiplot, you can appreciate the residual distribution for each model, but where the distribution is grouped up, it is divided in a group of species. The only thing that I want to underline is that usually the most difficult equation to learn is the temperature equation. This is not surprising. This is not surprising because in general, the heating and cooling process involved in the temperature evolution are quite complex. And we can say, qualitatively speaking, that the temperature evolution equation is the most complex one. Of course, to validate the trained model, we need to compare with classical procedural solvers, and we did it. We compare our models, our trained models, with the results obtained with a software that is called Chrome, and is a very used software in astrophysics if you want to solve the chemistry. This is for 3 models, the distribution of the relative errors, and if you want numbers, I put in this table the quantile of the relative errors, and you can see that the accuracy is not very good. We are not ready to replace a procedural solver with our models, but with this proof of concept work, we won a project in the Italian Supercomputing Center. So now we have much more computational time to push the training, also to explore a bit the hyperparameter space, to change architecture, and we are quite confident, we are doing it right now, quite confident that the accuracy of our model can be improved significantly. For now, for the molecular general case, for example, we have good error just in the 50% of the testing point. That is not enough. In terms of efficiency, we are quite happy in the sense that our model, respect to the procedural solver, have a speed up of a factor 90. That is good and can significantly improve the simulation speed. We also, of course, we solved with this model, we can solve the load balancing problem because we are not anymore dependent on the state of the gas. For the computational time required is not dependent anymore to the thermodynamical state of the gas, of course. So this is solved. I want to go more in deep in this error analysis. These are plots in a initial temperature, initial number density plan to see how the error are distributed, and possibly to see if there are interpretation and where we can and how we can improve our models. As you can see, for the equation that regulates the number density evolution, we fail to reproduce to predict good values at low density. So probably we have, and now we are working on give more attention to this low density tail, let's say. For the temperature, we fail to reconstruct the evolution at high density, and so we are also working on that. Our model is not the only emulator in the market, in the sense that there is also another one performed by some colleagues with which actually we are collaborating, Tommaso Grassi and Stefano Bovino, in this. They present in this paper of 2021 an emulator for chemistry that was completely different. I don't want to go in details. However, just a few words. They use an autoencoder to compress the information of a relatively large chemical network in a latent space, in which the real chemical network is represented with the smallest one. Then they solve the ODE system associated to this latent network, and then decode the result in the decoding phase, and then see what's happened. Using a pre-computed database of solution, they optimize the autoencoder to reproduce the good results. So there are significant differences between the two approaches. In their case, they need, of course, a data set. We don't need, even if we can add a data-driven part to the loss function, but it is not necessary in theory. They have in their work, they have a larger chemical network. They use 29 species, so that is much more massive with respect to ours. However, they have not the temperature evolution implemented. This is crucial. In fact, we are collaborating also to see if it's possible to generalize their model with a temperature evolution, because you know, as I said, the reaction rates depends on temperature. That means that the matrix element, the element of the representative matrix of the ODE system in general are temperature dependent. In their case, they are able to compress this information also because the matrix elements are just scalars. So it's not clear if it's doable to generalize. However, a potential application in some particular environment in which temperature don't vary, I don't know. In terms of average error, we are comparable, so more or less the same accuracy. That is not enough to replace a procedural solver in state-of-the-art simulation if we want to see what happens in the space for real. And also the speed up is the same order of magnitude. That was the work that we did, but now we want to improve, and what we are doing now is to construct a model that actually can work in the context of molecular cloud simulation. Remember, molecular cloud are the places in which stars born. In particular, what we need is to couple the trained model with the AMR code. Ramses is an hydro code that contains also on-the-fly additive transfer. In fact, it's called Ramses RT. So we rebuild the trained model in a compatible way, and we tailored the physical parameter of our model, like the initial condition for temperature. In other words, the physical parameter space in which our model has to work to exactly to past molecular cloud simulations. We had the variable radiation background, and I will spend a few words on that because it is particularly important. And what we are doing now is trying to optimize the neural network architecture to varying some hyperparameters, stuff like that. Let's spend just 2 minutes on radiation, because if you remember what I told you before, I said that in our proof of concept work, the radiation background was pre-computed. However, in a molecular cloud star form, and if you have a star, star emit light, and the light interact with the interstellar medium, and in general you don't know a priori what is the intensity and also the spectral shape of the light that arrive in a particular gas cell. So what we did is the following. We have in our chemical network 9 photoionization and photoheating reactions. So we discretize the electromagnetic spectrum in 10 frequency beams in a way in which every radiation is covered by a particular beam of radiation, and every beam can have a different intensity. Depends on the shape of the type of star that we have, and on a lot of stuff. So we have to promote the photorays from scalar, before that was just scalars, to function. And these photorays became function of this U. This U is the radiation flux in terms of number of photons per centimeter square per second. This is a important generalization of our model, because if we have 10 frequency beam, this means that our model have 10 more dimension in the input space. So now it changed. And what we are training now, the model that we are training currently in these days, are stuff that take time, initial condition, and photon flux, and give us the same quantity. So number density evolution for each species and the temperature evolution in time. Overall, so we have 21 dimension, and this is also one of the reasons why we choose to approach the physics for neural network in the literature. There are cases for PD solution in which it's shown that this kind of algorithm doesn't suffer a lot of the curse of dimensionality, and this is also what we found. So, and we are working on that, and when this model will be ready, finally we can apply it to simulations. We are very close to do it, and that's almost all that I want to tell you. I left you with a summary in the case if someone missed some key part. That's it. Thank you.
Okay. Okay, great. Thank you so much, Lorenzo. Maybe we have some time for a few questions from the audience. So, okay, maybe to break the ice, let's start. So as far as I understood, you basically your dynamics is made up of 3 components, and for now you're focusing on the chemical part, and for this chemical part you're using the PINN. Is it correct? So I was, yeah. So and basically this is your fast dynamics. So usually when there are systems which have different hierarchies, people divide the variables in fast variable and slow evolving variables. But for instance, the chemical part could be understood as a quasi-static transformation. So that you first evolve the chemical part, and then you feed in the other layer, which when you evolve in time and you feed in again. Instead, here you're trying to put everything together.
Yes, we are trying to put everything together. However, maybe it's better to go back one of the first slide. Here. Okay. I want to remark 2 points. The first is that if we want to follow the full chemical evolution, it is expensive, and this is the motivation why we want to use emulators for that. The other point is that, of course, it's possible to don't follow the full evolution, the full non-equilibrium evolution, but to approximate the chemical evolution in a kind of equilibrium state. But there are works that show that you can have quite different result. And this is true in different environments. In particular, in giant molecular clouds, the problem is that the cooling of the gas that is necessary to create denser and denser region in which stars can form depends strongly on the chemical state, and you have to be very precise in that, because if not, your theoretical simulation doesn't fit with the observation.
Okay, so I was wondering, can one identify regimes when maybe one can activate or deactivate certain equations? Because, for instance, when the cloud of gas is still expanded, then in this case, for instance, it wouldn't make sense to look at some of the, I don't know. It would make sense to look only at a subset of these four equations that are here. And then it's when the gas is contracting. And so instead, in this case, one needs to take into account more effects. So I was wondering whether it is possible to distinguish different regimes in which the approximation of removing one equation is not valid anymore.
Okay, it is theoretically possible. However, if it's difficult to define the correct regime, because just to give you an example, if you want to follow the radiative transfer, okay, the interaction between the photons and the matter strongly depend on the chemical composition. Different chemical species have different cross-section. Just imagine the ionization state in which you are. If you have neutral hydrogen, the interaction between matter and radiation is much stronger. The cross-section is order of magnitude bigger. So it's, to answer to your question, is probably there are some regime, maybe when the ISM is fully ionized, in which you can switch off some equation, but I suspect that you can't cut a significant part of the computational time doing this, and I'm not sure that you can control well the simulation. You don't know what can happen.
Okay, yeah, I think you're right. It's difficult to control. Also, like I was thinking that maybe one can add tuning parameters in front of these equations, and then one follows the value of the tuning parameter as a function of the error of the cost function. And so that could in principle be possible to highlight these different regimes of this different level of estimation. But yes, I mean, it could be,
it's good.
As you said, it can be computationally. That's okay.
Yes.
Okay. We have a question from the audience, Carlos.
Hi, I wanted to ask in particular about the adaptative weights of the residual. Can you go a bit more in detail how exactly? Because I've seen some papers using like neural tangent kernels, and say what method did you use for like adjusting those weightings?
Okay, good question. And also because now we are changing the algorithm actually that is doing that. This is I don't remember the exact name of the algorithm that we used. Is something like Relo Bralo, stuff like that. Relative balance of the, I don't remember what it means, but in a few words, basically every given number of epoch, you control the value of this two norm of each terms of the loss function, both for initial condition and for the internal part, and try, and every like 100 or 1000 epoch, you adjust this weight in a way in which you have the same order of magnitude for the residuals. It's not something that is very tricky. That is the maximum, the best thing that we have in mind to do.
Awesome. Thanks.
If you want to check the algorithm details, you can find Relo-Bralo algorithm.
Awesome. Thank you very much.
You're welcome.
Okay, do we have more questions from the audience? Oh, okay. Well, so if not, let's thank our speaker again, Lorenzo. And again, apologies for everyone for the technical problem that we experienced today. Also, Lorenzo, thank you so much for your patience and with the delay. We deeply apologize for that. So simply we didn't expect. Usually our experience with the seminar goes smoothly.
Don't worry, as I said before, technology is not an exact science. You never know what can happen.
Okay, cool. Well, so okay, thank you so much, everyone, and we'll see in a couple of weeks' time with our next speaker.
Bye, and thank you again.
Our pleasure. Thank you.